So good morning. I'm from the team JECC from Techno. The Robotour was last year. And our robot Fesl, it was the big one, maybe you remember, was the big metal box containing the PC. Yes, what to say without pictures. One special feature of our robot is that it's nearly completely waterproof by design. So we use waterproof USB connectors, waterproof serial connectors, waterproof power connectors, so the rain can just come down and we don't need any fancy foils or umbrellas around it. So that's very relaxing. You don't have to care. The robot won't be damaged. So at least it is rain protected from rain coming down because I have some cover over the camera. Yeah, but it works quite well. So no issues with the rain. What's to say? So last year on the Robotour, I think many of you remember, there was very, very heavy rain, and then the robot was not completely waterproof, and then the water found one way to destroy the compass. That's why we had a lot of problems last year, but for this year everything is really good from the mechanical and hardware shape. So,
maybe I can ask, would you agree with Jirka, as he was saying, that instead of testing or testing time, this worked out in the first place? Did you also do a lot of testing? So
yeah, we had a lot of testing the last few weeks in our park in Deggendorf. The Robotour was last year, so we went out nearly every two days in the afternoon and had 2 hours of testing. And there you can fix a lot of trouble and you can change a lot while being relaxed and not just before the competition. But one problem I had, I didn't read the rules that exactly, so I wasn't aware that the robot could return after unloading back to the base. And just that's fine to pick up the barrel, unload it, and then everything is good. Then someone told me, hey, if you return to the base, you get another point. And then I changed the code quickly, and then I had a bug in it. And that what prevented, maybe prevented the first place, I don't know. But the problem was that the robot then wasn't aware to stop in the unloading station because of the status of the barrel switch where it detects the barrel. So it was a bit of a pity, it was just some false through mix up, but yes. That happens if you don't do enough testing or don't read the rules and don't have enough time for testing. So, but then the other rounds were quite good. So, what were the problems? Other problems that we run over a very small robot, which we weren't able to detect because the laser scanner was mounted in some, this was mounted higher than the robot was actual height, so it came down in some very sharp angle, so we were not able to detect it. And also the camera just looks 2 meters in front of the robot. So it was the showstopper of one round. In the third round we had the problem. We went to this unloading station, which was very far apart, where there was all the muddy. There was a lot of mud around the road, and their neural network failed a bit, but it was enough that it take too much of the crossing, and all 4 wheels came out, and then it was over.
So my question
question from a different part. I know that there's quite a lot of computational power on board, right?
Yeah.
What is in there and how long does it last with the battery?
There's a CMD inside with 8 cores and 16 threads at 2 gigahertz, so quite powerful. I'm trying to spread the work across as many cores as possible, so I have one high-loaded core, but all the other cores are just at 10% or so there's much room left for additional features. And what I'm also using is AVX2 vector intrinsics to speed up all the work, and that it depends how much you can put through the memory, through system memory, but you can get a speed up of 6x or something like this. But the code gets very ugly if you're writing that AVX stuff, so when you could write one equation you would bring in one C line, it's about 20 lines or so of AVX code. It's just images.
And the battery?
The battery lasts for, when the battery was still good, it lasted for 2 hours. And now it's about 1.5 hours. So that's good. This one?
No, you don't know. It's auto advantage.
The first one.
Okay.
Yeah, the second line.
Okay. Okay, it looks okay. I can control it with my. Okay. So that's the robot. Here we see the ugly lead acid batteries. So no money for good accumulators. In this box there's the PC mounted. That's the steering. So the base of the robot is some Chinese pocket quad for children. And the steering is really heavy, and I tried a lot of motors and nothing worked. And then I bought the servo motor from the Renault Clio 2. And it wasn't also that powerful that we added an additional reduction with the chain. And it's just a motor without any sensors. And I added a magnetic encoder on the top because it's rainproof and doesn't wear off because of scratches. And there's a magnet glued on the X. It's a very nice encoder. It's in an SO8 package. You get it from AMS. It's really cheap, and it just you put ground 3.3 volts, and it puts out a voltage proportional to the rotation angle of the magnet, and it does all internal compensation. If the magnet is a bit off, it's really nice. You can use it as a potentiometer. These are all the waterproof connectors. So that's USB. This is RS422 for communication with the motor controller and reading data from the LiDAR, and for communication with the compass. So it's also nice with the RS422 because it's differential signaling, so you don't have issues you have with Europe or something like this if we have long cables and the currents from the motors. So that's working really stable. And the box down here, there's the motor controller. It's a custom PCB we made. There's an STM32 on it and 2 Texas Instruments motor drivers, so everyone can do a peak current of 14 amps. And they read back the angular sensors and the speed sensor from the motor and do all the read time control, and it's communicating with the PC over RS422. So on the top there's a GPS antenna. It's a Robotour, and they have some special antenna geometry which suppresses all the reflections coming from buildings or from the surface gets wet, the reflections get gets stronger, so that's working quite nice. I had very good GPS signal even under the bridge. It was accurate to 1 or 2 meters, and it's connected to a simple Chinese U-Blocks 8 module, and that works quite well.
Objection, that's a Swiss module.
Sorry?
That's a Swiss module, not
the module was Chinese and the chip inside is Swiss. On the left side, there's the compass inside, and it's not a MEMS-based compass, it's a flux gate compass, which works. There's a magnetic core inside, and it gets magnetized by some stimulating coils. And then there are 2 windings outside, and with that you can measure the strength of the field from any direction. And for tilt compensation, it's suspended in some liquid so that it's always in tilt. And it's working quite nice, very precise. It doesn't decalibrate and nothing because there's no accelerometer picking up some vibrations. But it's quite slow, so it takes the damping, I set it to 3 seconds until it gets to a new full scale. And while the robot is shaking because of the liquid, it's a bit oscillating around the center, but the true center is very accurate to 1.5 degrees or something like that. So very nice compass. But because it's so slow, I just use it for global planning. Together with the GPS data and the data from the map. And for the local planning, where I create my occupancy grid, I use the visual olometry from the camera. It's this one. It's a stereo camera from Stereo Labs. And they run all the depth computation on the GPU. And because I have a GPU in it for the neural network, that's quite fun. And it gives very good depth data. And it goes up to 20 meters, so that's very, very nice. Then what I also did, I added 2 Realsense cameras from Intel on the sides, but I didn't use them this year. I just collect the data for training a second neural network for next year, so that I can have a view closely around the robot for driving backwards and also to avoid small obstacles or other small robots. And yeah, we'll see if that works. So that's the box with the computer inside. So the main processors under here, it's just a computer module which contains the processor, the system memory, and an SSD, and it's plugged into some carrier board. And all the PCI Express and USB lanes are brought out over a high-density connector. And yeah, so the graphics card is connected via PCI Express to the module. And I'm using a Minuel DC-DC converter with about 200 watts to get 12 volt for the PC from the 24 volts of the batteries. And the PC does need some ATX supply. You just plug in 12 volts and it just works. So up there's the USB 3.0 hub and the RS422 controller with 4 channels. So it's...
How do you ventilate the box?
Sorry?
How do you ventilate the box?
Normally I have some gap open, and that's also good because it's rain-proof even if it's a bit open. But to get it completely waterproof, that you could wash it with some high-pressure cleaner, I will add some water cooling. So to put a water cooling block on the GPU and the CPU, so that you can bring out over waterproof pipes and add a radiator outside. And I got 2 nice fans from Robotour, which are completely waterproof. So that will be the work for next year. So that's the GUI. Up there you can see the input image coming in from the camera. The second one is the output of the neural network. That's the depth image. So that's for the OpenStreetMap planning. And that's the view. That's how the robot creates the local grid around the robot. So I've used the output of the neural network together with the depth data and created map. And by the visual odometry, I can track all the points, and I'm tracking I can track up to 1 million obstacle points. 1 million for the camera, 1 million for the SICK. Here you see the usage of the grid. So would be much more place, or I could even make it smaller to handle less obstacles or obstacle points. But I think it's just fine. I can do it with the AVX stuff. I can do it on about 4 to 6 cores. I can do it in about 60 milliseconds. So that's just fine for now. So, and up here you see the solid line. It's the heading to the next target used by the OpenStreetMap data, GPS, and the compass. And it now tries to plan its trajectory to get as close as possible to the next target. And when it glides somewhere, so it brute forces actually all the possible steering angles, because I have just Ackermann steering. It brute forces all the angles and stops if it hits some target. And then I'm looking which of these possible steering angles gets me as closest to the destination, and it just takes this one and sets the steering angle. So that's no closed loop control, just always testing which one is the best. Any questions on that?
Not the white points.
The white points, it's the trajectory of the robot. So that's all the test points where it tests for a collision.
Do you start turning before the junction or in it?
It starts turning before the junction. So the junction would be actually here. And it starts turning over here.
And is there some like fixed distance how far in advance you start turning? Or?
I'm changing you mean this one?
Yeah.
I change it about 10 meters before the actual junction. And
So
here
you
it's
make many waypoints during the pass.
the waypoints that are in OpenStreetMap, so I don't use any additional data, it's just a plain OpenStreetMap. So what I'm also doing, if the trajectory is planned as long as a collision, and if there's no possible way and it gets too short, maybe 1 or 2 meters, then I switch to some very simple bumper mode where I place 2 virtual bumpers over here, and they just push away the robot from some possible target. You see very often before it turned into a junction, it made a bit like it was drunken. It was just because it was pushed around by the bumpers. But that's very simple and very quite stable. So it worked very well. So which is always
It cannot show this.
okay.
We don't know why. We don't know.
Because these are the pictures of the neural network, what went in and what came out. They're quite interesting sometimes.
Move from browser out.
Firefox or use Firefox. Maybe Internet Explorer. It's always working.
But it seems there is really something wrong.
Máš tamhle ještě webudovat Firefox a setup.
No, it's not from mine.
Okay. Try. You know.
Yes.
Okay. So the neural network is trained to detect drivable surface, all the obstacles, and what I also did, I trained it to detect people, cars and bikers, because I plan to do some higher level stuff with this data, maybe giving some acoustic sign if people are in front of the robot, or maybe being slower when there are people to slow down the speed. So that's why I put this into the training data. So the neural network is based on Microsoft ResNet, which was originally meant just for image classification. But the last fully connected layers, which do some classification tasks, they are skipped. And there's one additional convolutional layer, which picks up all the pixels from the feature map, and then the neural network directly outputs one matrix of all the classified pixels. So it's not patchwise, but the neural network looks at the whole image and then outputs the segmentation. And the segmentation is 1/8 of the input resolution. So I'm going in with 640 by 360, and there's coming out 80 by 45 pixels. And that's enough resolution to navigate and detect all the roads and people and so on. And it's running quite efficiently. So I have a GTX 960 inside, and this graphic card would be able to push about 30 to 40 frames through the network, and I synchronized it with the camera, so I'm running at 15 frames per second, which would be also enough to drive quite fast. So. Yeah. Any questions?
Are you somehow distinguishing the different types of obstacles, like pedestrians and grass?
Not now. So that's what I plan to do an extra safety distance, maybe around persons, or then go slower if there are many persons.
So you place everything to the grid map?
Yeah, everything is placed. What's not drivable in the grid map. Also, the laser scanner data is put into the grid map, and that's it so far. But especially for the competition in PSEC, where are so many people, it would be nice to just drive slow, or give some acoustic sign to bring the people away, and some very loud horn.
More questions? Is there like one, I don't know, sensor hardware algorithm that you like say that made your robots win the second place? Like, is there one thing that you can say that that's why my robot is working so well, or
I would say
suggestion for other teams, like, you know, try to use next
I would
year
say it
this
worked
one
that
thing.
good because there's no really special stuff, but everything works good together and everything gives good results, and combined with all that's, I think that's it. So there's no really special killer feature.
Yeah,
I mean-
the killer feature is that all parts work
Together,
Yeah.
I mean, the neural network is very nice. You can put something on your robot, do it, because it gives a very good segmentation output, even if the road gets a bit muddy or something like this. Okay, there are some locations where it doesn't work that well, but as I log every picture the robot takes, I can retrain the network at home, so it gets better and better with every competition or with every test run. So you don't have to change the algorithm, you don't have to screw some parameters which work there and don't work there, and it's very stressless because it just works.